for each of us. Now I invite her to give a brief introduction of the program and deliver the welcome address.
Principal of the college, Dr. Verghese Matthew sir. Keynote speaker of the day, Dr. Indulal ji, participants from different parts of the country, and my dear colleagues. It gives me great pleasure to extend a warm welcome on behalf of Dr. C.T. John Research Center for Mathematics, Marthoma College, Tiruvalla. The Research Department of Mathematics organized this research-oriented lecture series with the intent of promoting active and interactive learning. We wish this lecture series will enable you to enrich your knowledge. Our principal, Dr. Verghese Matthew sir, is with us. He was the former head of the Department of Mathematics. Because of his continuous support and guidance only, we are able to conduct a webinar like this. With great pleasure, we welcome you, sir, to the online lecture series. Our keynote speaker is Dr. Indulal ji, Associate Professor and Aloysius College. He has done his research in Studies on the Spectrum and Energy of Graphs from Cochin University of Science and Technology. Dr. Indulal is the referee for various journals and approved reviewer of American Mathematical Society. Indulal sir is also the member of American Mathematical Society, Kerala Mathematical Society, and American Chemical Society. He has more than 15 papers in referred journals. Also, he has presented research papers in seminars and symposia held in different parts of the world. On behalf of Marthoma College and all the participants, I extend a warm welcome to you, sir. Today, we have with us teachers from different colleges, research scholars, and PG students. We welcome all of you to the online lecture series. I also appreciate the organizing committee members for coordinating the program and welcome you all to this lecture. Thank you.
Thank you, Ms. Without the able support and leadership of our principal, Dr. Verghese Matthew, this program would not have been a reality. I'm happy that he is gracing the occasion, and I gladly invite him to deliver the principal's address.
Today's chief guest, Professor Dr. G. Indulal, St. Aloysius College, Alathua. Professor Minnie Thomas, Head of the Department. Professor Anu and James, convener of this program. Organizing committee members, Professor Rajesh, Professor Manish Jacob, Professor Prida Rachel George, research scholars, teachers from various colleges, students, and other participants. Greetings from Marthoma College, Tiruvalla. The Department of Mathematics, Marthoma Tiruvalla offers UG, PG, PhD, and one certificate program. The department has a full-fledged research center, Dr. C.T. John Research Center for Mathematics, named after the former faculty of the department. So far, the research center has produced 16 PhDs. Now, 11 scholars are pursuing their PhD program in mathematics. Every year, we conduct Professor C. Kochiman Memorial Endowment Lecture. Dr. C.T. John and Professor C. Kochiman of the department has initiated the formation of the Kerala Mathematical Association. COVID-19 pandemic has affected all our activities. Only alternative for education sector is classes through online platforms. Recently, Department of Mathematics has organized two major activities. First one was online 3-day national lecture series on graph theory and its applications. Professor S. Anubhagam was the resource person. Second one was a 6-day international workshop on initiation to linear algebra. It was from 28th September to 8th October 2020. In continuation to linear algebra workshop, now we have another research-oriented lecture series. We are planning to conduct 2 or 3 lectures in a month on this lecture series. The aim of the lectures is to introduce new research areas in discrete mathematics, especially graph theory. Today we have an important person with us, Dr. G. Indulal. He is from St. Aloysius College, Erathu. He got PhD degree from Cochin University of Science and Technology under the guidance of Dr. A. Vijaykumar. He has several publications. He is a member of PG Board of Studies in Mathematics, Mahatma Gandhi University, Kottayam. He is an orator and encouraging mathematical education. Dr. Indulal is an expert in the field of spectral graph theory, which uses the tools of linear algebra. On behalf of Martha College community, I welcome you, sir, to Martha College Thiruvalla. I congratulate the Department of Mathematics for this new initiative. Participants of this program are our source of inspiration. I welcome all participants to Martha College Thiruvalla. I am very sure that the research or the lecture series will be a platform to learn new areas in discrete mathematics. I wish all the participants a nice experience. Hope the discussions and deliberations will generate interest towards spectral graph theory. Wish you all the best. Thank you very much.
Thank you, sir. Next, we move on to the first session of the lecture series. Before that, I would like to inform that the second session of this series will be conducted on Saturday, 17th October, and the link for the same will be sent later. We are extremely pleased and honored to have an understanding of the topic. I invite you, sir, for the talk.
Okay, thank you very much for the introductory remarks. And at the outset, let me thank the organizers, especially Dr. Varghese Matthew, Principal, Martha College, Thiruvalla, for inviting me to give a lecture on this prestigious C.T. John Memorial lecture series. And during his presentation, he remarked that there are several milestones already initiated by the Department of Mathematics and Martha College, Thiruvalla. And I congratulate all the team members behind this organization. And once again, thank you very much for inviting me to this lecture series. And I assume that all participants have a graph theoretical background. And even though they do not have, I suppose they have a linear algebra basic background. The last week, Martha College Thiruvalla conducted a workshop on linear algebra. And this topic, this lecture on spectral graph theory uses plenty of linear algebraic tools. And without the linear algebra, we cannot have discussions on spectral graph theory. So we assume either you have a graph theoretical background or linear algebra background. As all of you are aware that this graph theory is evolved as a branch of mathematics in the 18th century. And I avoid the cliche statement that due to the work of Euler, Leonhard Euler on the famous Königsberg Bridge problem. And after its evolution in the 18th century, graph theory became dormant for about that century. And initiation of its development started only in 1860s and later on 1890s, etc. And this branch of mathematics, spectral graph theory, evolved around the 20th century in the early 1940s. The first paper on graph spectra, the spectrum of graphs, or a paper related with the spectrum of graphs appeared in 1936. And in that paper, the chemist E. Huckel uses some spectral graph theoretical concept to describe his Huckel molecular orbital theory, particularly related with the energy of the molecule saturated hydrocarbons. And it took around 21 years later only. So it took 21 years for a mathematical paper on spectra to appear. The first mathematical paper on spectrum of graphs appeared in 1957 due to the work of Sigowitz and Collatz. And now it is 2020 and around 63 years have been passed. And during these 63 years, more than 15,000 research articles have been published in one aspect or other dealing with the spectrum of graphs. So this is actually an ocean of research results. So those who want to pursue or to initiate research, this is an ocean of results. So that one can attempt or continue or do some research on already established results, generalizing it, deviating that from the normal approach, so and so. So that is why the spectral graph theory is a significant area of research. And as the name suggests, I would like to talk with you by sharing some information regarding the spectrum of graphs. See, I am not going into the core level at the first lecture. Instead, I would like to give you a very, very elementary level talk, elementary level information sharing, with discussing the tools we are applying in this study of spectrum of graphs. As I already suggested, we use plenty of linear algebraic tools in this discussion. And we start with at a very elementary level. Is the screen visible? I can't see the chat.
Yes, sir. Yes, sir.
Okay. So we begin with, see, usually members of Rn, the Euclidean space is denoted by the ordered n tuple x1, x2, x3, etc., xn. And in our discussion, we denote the members of Rn as n by 1 column matrices. So that X is a member that is represented as an n by 1 column matrix. And we define dot product of two vectors. The members of Rn are called vectors because Rn is a well-known vector space. Members of Rn are n by 1 column vectors. And dot product of two vectors is defined as, say, if x is equal to x1, x2, etc., xn, and y is equal to y1, y2, etc., yn. The dot product x dot y is defined as x transpose y. So this is sigma I from 1 to n xi yi. And x dot x, that is sigma I from 1 to n xi square. So that this is never 0 if x is not 0. And two vectors are said to be orthogonal if their dot product is 0. And the linear independency of vectors follows from basic linear algebra. And two orthogonal vectors are always linearly independent. So if u and v are orthogonal, u dot v equal to 0. And if you consider a linear combination alpha u plus beta v equal to 0, taking dot product with V, alpha u dot V, this will be 0, and beta V dot V equal to 0. That implies beta equal to 0. Consequently, alpha equal to 0. So orthogonal vectors are linearly independent. And actually, this is the place where linear algebra comes into the theory of graphs. A non-pictorial representation of graph is affected by an adjacency matrix, by means of a matrix. See, there are several matrices associated with the graphs. Even though the initial one which started during the work of Haeckel on his molecular orbital theory was the adjacency matrix of the corresponding molecule or the corresponding graph. There are more than 95 matrices now associated with the graphs. Adjacency matrix, distance matrix, Laplacian matrix, signless Laplacian matrix, signless distance Laplacian matrix, complementary distance matrix, reciprocal distance matrix, cycle matrix, block matrix, and whatever concept you meet in graph theory that can be converted suitably in terms of a matrix. So that is the practice actually now going on in the research area of graph theory. And a non-pictorial representation of graph is affected by a matrix, and the adjacency matrix is defined by, there is an n by n matrix. If G is a graph, if G is a graph on vertex at V1, V2, etc., Vn, then the adjacency matrix A is defined as an n by n matrix whose ijth entry is 1 or 0 according as Va is adjacent to Vj or not. So actually this adjacency matrix then reflects the adjacency relation in the graph. We can construct the graph from the adjacency matrix and vice versa. So this serves as an efficient tool for inputting a graph into a computer and for machine software works. Now, this is a natural question that whether labeling of vertices has something to do with the adjacency matrix. Because we defined adjacency matrix with respect to a particular labeling, and the ijth entry is 1 or 0 according as that particular, under that particular labeling, Va adjacent to Vj or not. Let us see what happens if we interchange two labels, say 1 and 2. See, in this graph, this is K12, vertices are labeled 1, 2, 3. This is also K12 with vertices labeled 1, 2, 3. Whereas we interchange the labels 1 and 2 in the second graph. And how this interchange get reflected into the adjacency matrix? See, we can see that for the first one, this is okay. So these rows and columns are indexed by vertices. And in the second adjacency matrix is adjacency matrix of K12, but at the first look they are different. But what happens actually is, when we interchange the 1 and 2, 1 and 2 designated with first row and second row, first column and second column. Now, in this second adjacency matrix, the first row and second row get interchanged. So 0, 1, 0. So this happens first. First and second rows get interchanged. And these are indexed by columns also. So these two columns get interchanged. And this again, these two first and second columns get interchanged, and that results in 0, 1, 1, 1, 0, 0, 1, 0, 0. And we can say that that is the next second adjacency matrix. And from elementary matrix theory, we see that interchanging of two rows is an elementary transformation. Interchanging of two columns is an elementary transformation. And a matrix obtained from another matrix using elementary transformation is similar. So what we are getting is a similar matrix. So if under one labeling, if A is an adjacency matrix, and in another labeling, B is an adjacency matrix, then A and B are similar. here we applied interchange of two labels, and now you consider a general shuffling of this labeling, so that v1, v2, etc., vn get changed labeled to u1, u2, etc., un. Then in algebra terms, this is a permutation, and we know that every permutation is a product of transpositions. So this is a product of transpositions. And when this product of transposition is applied on this matrix, at each transposition, two elementary transformation will happen. Interchange of two rows and interchange of two columns. So consequently, this product of transposition results in a series of elementary transformation in the first adjacency matrix A, and at last we get to B, and A and B are similar. So if we are interested in studying the properties of matrices which are invariant under similarity, labeling is insignificant. I repeat, if we are interested in studying the properties of matrices which are invariant under labeling, which are invariant under similarity, then this labeling is insignificant. And in spectral graph theory, we are interested only in those properties which are invariant under similarity. So no problem. So you need not stick on a particular labeling. You can label the vertices in any way as we wish. What we get is the adjacency matrix. And if somebody get another adjacency matrix, then both these are adjacency matrices are similar. Okay. And adjacency matrix keeps similarity under vertex labeling. And one of the most interesting facts is A is real and symmetric. A is real because the entries are only 1 or 0. And the matrix is symmetric because Aij depends upon whether Vi and Vj are adjacent. So that is the same as Aj. If Vi and Vj are adjacent, Vj and Vi are adjacent on the other way. Otherwise, they are not. So Aij is equal to Aj, and that is symmetric. See, actually, this is an advantage of you considering this adjacency matrix. Then we have plenty of results concerned with the symmetric matrices in matrix theory in linear algebra, and we can use all those results available in linear algebra to study the properties of the adjacency matrix. And another interesting observation, see the row sums to degree, that is trivial because corresponding to one row, Vi, see the entries coming along that row is, if somebody is adjacent to Vi, the entry will be 1 and elsewhere zeros. So how many ones are there? There is a total number of vertices adjacent to Vi. So this row sums to degree of Vi. This is very trivial. Another observation is ith entry of A raised to K is the total number of Vi, Vj walks of length in G. And actually, you see this result. The A is the adjacency matrix of a graph G. And this matrix is another language representation of G. And this result then gives a structural relation or structural property of the graph in terms of the corresponding matrix. See, actually, the total number of Vi, Vj walks. See, walks is a structural property of the graph. The ith entry of A raised to K is the total number of Vi, Vj walks of length K in G, and the proof can be seen in any elementary graph theory textbooks. And for the completion, for the sakeness of completion, let me sketch the proof. See, for K is equal to 1, the result is very trivial because the ith entry of A raised to K, A raised to 1, that is A, that is Aij. If Vi and Vj are adjacent, then the number of Vi, Vj walks of length 1 is 1 and 1 is Aij. If Vi and Vj are not adjacent, then there is no Vi, Vj walk of length 1 and the corresponding entry is 0, and that is the total number of Vi, Vj walks of length 1 in G. And assume that the result is true for K minus 1, so that the ith entry of A raised to K minus 1 say matrix Bij is the total number of Vi, Vj walks of length k minus, and a raised to k, let it be Cij, and matrix Cij is equal to then matrix Bij into matrix Aij, where Cij is sigma h from 1 to n Bih Ahj. See, consider one term, Bih into Ahj. Bih is the total number of Vi, Vh walks of length k minus 1, and Ahj is the total number of Vh, Vj walks of length 1. So the total number of Vi, Vj walks of length k passing through Vh is Bih into Ahj. And as h runs from 1 to n, this gives the total number of Vi, Vj walks of length k in G. And by induction, then the result follows. And we define the eigenvalue. Let's say, this is the conventional definition of the eigenvalue and eigenvector. If A is a matrix, then lambda is an eigenvalue of A. If and only if there is a non-zero column vector V such that AB is equal to lambda V, and the set of eigenvalues of the graph or the corresponding matrix are the roots of the characteristic polynomial determinant lambda I minus A, and the set of eigenvalues forms its spectrum. Regarding a graph, we see that the adjacency matrix is symmetric and real. Then we can see that the eigenvalues are real. A is real, so A conjugate is A. A is symmetric, so A transpose is A. So suppose lambda is an eigenvalue of A with an eigenvector V, so that AV is equal to lambda V. Then lambda V bar transpose V is equal to V bar transpose lambda V. This is V bar transpose. See, this lambda V is AV. This is V bar transpose. See, this A can be written as A conjugate because A conjugate is equal to A. And this A conjugate can be written as A conjugate transpose because A conjugate transpose is A itself, V. And this is A conjugate, V conjugate, the whole transpose V. And since AV is equal to lambda V, AV, see, and this is AV, the all conjugate transpose V. AV, the all conjugate is equal to lambda bar V bar. So this is lambda conjugate, V conjugate transpose V. And we started with lambda V conjugate transpose V, and we ended with lambda bar V conjugate transpose V, and V is non-zero because V is an eigenvector, and V bar conjugate V is equal to sigma I from 1 to n Vi bar Vi, if V is equal to V1, V2, etc. Vn. And this is modulus of Vi square, so this is sigma I from 1 to n modulus of Vi square, that is never 0 because V not equal to 0. And from this equation, then lambda equal to lambda bar, or lambda is equal to lambda conjugate. So eigenvalues are real. So the eigenvalues of a graph are always real. And another observation is, this is also from elementary linear algebra. For every eigenvalue lambda of A, f lambda is an eigenvalue of f of A for any polynomial fx. See, we use these results in discussing our major results later. So you consider any polynomial fx. So suppose f of x is equal to an x raised to n plus an minus 1 x raised to n minus 1 plus etc. plus a naught a1 x plus a naught be a polynomial in x. Then it's given lambda is an eigenvalue of A. So there is a non-zero vector V such that AV is equal to lambda V, V not equal to 0. Therefore, A square V is equal to A of AV. This is A of lambda V. This is lambda of AV because lambda is a scalar. So this is lambda of lambda V, and this is equal to lambda square V. So reasoning inductively, we have a raised to TV is equal to lambda raised to TV for all t, 1, 2, 3, etc. Now f of a is equal to an a raised to n plus an minus 1 a raised to n minus 1 plus etc. plus a1 a plus a naught I. And when we apply v on both sides, fa of v, we can see that an a raised to nb, a raised to nb is lambda raised to nb plus a n minus 1 etc. a1 lambda v plus a naught v. So v is taken outside. What happens is then v is taken outside. So this is of v, and this is nothing other than f lambda. F lambda v. So for any eigen lambda of a, f lambda is an eigenvalue. For any polynomial f of x is an eigenvalue of f of a for any polynomial fx. And this is another interesting observation regarding the eigenvalue of a graph. The algebraic multiplicity of an eigenvalue is equal to its geometric multiplicity. What is meant by that? The algebraic multiplicity of an eigenvalue is the number of times it appears as the root of the characteristic polynomial. And associated with an eigenvalue lambda, there are eigenvectors. There may be more than one eigenvector. The number of linearly independent eigenvectors associated with the lambda is known as the geometric multiplicity of lambda. The algebraic multiplicity is the pure algebraic multiplicity, that is the number of times lambda appear as the root of the characteristic polynomial. And associated with lambda, there are eigenvectors, and the number of linearly independent eigenvectors, or the dimension of the space spanned by the eigenvectors, and that space is known as the eigenspace. So the algebraic multiplicity is the dimension of the eigenspace associated with the lambda. And since A is a symmetric matrix, we can see that the algebraic multiplicity of an eigenvalue is equal to its algebraic multiplicity is equal to its geometric multiplicity. So if lambda appears as the root of the characteristic polynomial k times, then there are k linearly independent eigenvectors associated with that. So suppose lambda 1, lambda 2, etc., lambda k are k distinct eigenvalues with multiplicities m1, m2, etc., mk. Suppose lambda is an eigenvalue of multiplicity k. Now we see that A is the matrix Aij, that is the adjacency matrix of G. And we can see that, or we can consider this A as a linear operator from Rn to Rn. A can be considered as a linear operator from Rn to Rn, so that the basis of, in some basis say u1, u2, etc., un of Rn, the matrix of A is A itself. So that A ui is equal to A I1 u1 plus A I2 u2 plus etc. plus A in un. Now it is given that lambda is an eigenvalue with multiplicity k for G. So there is a non-zero v1, non-zero vector v1 such that lambda a v1 is equal to lambda v1. v1 is non-zero. So if we take v1 alone, that is linearly independent, and consider the space capital 1 spanned by this v1 alone, and capital V2, there is a collection of all w such that w orthogonal to v1. Since Rn is having an orthogonal basis, Rn can be then written as the direct sum of v1 and v2. Say elementary linear algebra. Now we can show that this A can be a restricted linear operator from V2 to V2. This is because, suppose W belongs to V2. Therefore, W transpose V1 equal to 0. We can show that AW also belongs to V2. You take the dot product of AW with V1. AW V1 is W AW transpose V1. That is W transpose A V1. This is W transpose A V1 is lambda V1. Lambda is a scalar, so lambda W transpose V1, and this is 0. This is 0 means AW is also orthogonal to V1. And V2 is the collection of all vectors which are orthogonal to V1. So AW also belongs to V2. So A can be now considered as a restricted linear operator from V2 to V2. The same argument applies. Now lambda is the root of the characteristic polynomial k minus 1 times. When we consider A as a linear operator on V2. Then associated with this V lambda, there is another vector V2 not equal to 0 in V2. That means orthogonal to V1. Thus that A V2 is equal to lambda V2. Now we replace the argument by changing V1 to the space spanned by V1 and V2. And V2, that is a collection of all W which are orthogonal to V1 and V2. The same argument applies till we extract. So the same argument will apply till we extract k linearly independent eigenvectors, k orthogonal eigenvectors, and we already showed that orthogonal vectors are linearly independent. So this process will continue till we get k linearly independent or orthogonal eigenvectors associated with lambda whose algebraic multiplicity is k. See, from this stage, the occurrence of lambda ceases. Occurrence of lambda stops. So, the occurrence of eigenvectors associated with the lambda also stops. So, if lambda 1, lambda 2, etc., lambda k are k distinct eigenvalues of the graph with multiplicities m1, m2, etc., mk, then m1 plus m2 plus etc. plus mk equal to n, where n is the number of vertices of the graph or order of the adjacency matrix. Then here we showed that the algebraic multiplicity k is equal to its geometric multiplicity by systematically constructing k orthogonal eigenvectors associated with the lambda. And if we generalize this, then corresponding to lambda 1 with multiplicity m1, we get m1 linearly independent eigenvectors. And corresponding to m2, we get m2 linearly independent eigenvectors, which are in fact orthogonal to the already chosen m1 linearly independent or m1 orthogonal eigenvectors. All these are orthogonal because whatever we are choosing a new vector from in the space orthogonal to the already constructed VA. So at last, the construction ends with mk linearly independent eigenvectors associated with the lambda k. So in the n-dimensional space Rn, we get m1 plus m2 plus etc. plus mk, which is n linearly independent eigenvectors. They are linearly independent. They are not only linearly independent, they are orthogonal also. So we get this set of n linearly independent eigenvectors consisting solely of the eigenvectors of the graph constitute a basis for R. And this is a strong result in spectral graph theory. Given a graph G, the eigenvectors of G constitute a basis of R. And we can see that in that basis, Suppose lambda 1, lambda 2, etc., lambda n be the eigenvalues with actually, in fact, with the multiplicities. See, some lambda 1 and lambda 2 may be the same, and v1, v2, etc., vn be the orthogonal basis formed by the eigenvectors of these lambda 1, lambda 2, etc., lambda n. Then we can see that av1 is equal to lambda 1 v1, av2 is equal to lambda 2 v2. So this is lambda 1 v1 plus 0 v2 plus etc. plus 0 vn. And this is 0 v1 plus lambda 2 v2 plus etc. plus 0 vn. And at last a vn is equal to lambda n vn. And this is 0 v1 plus etc. plus lambda n vn. So that the matrix of A, in this particular basis B is equal to lambda 1, 0, 0, etc., 0, lambda 2, etc., 0, 0, lambda 3, etc., etc., lambda n. So, given a graph G, Rn has a basis consisting of eigenvectors of G, and in that basis, matrix of the adjacency matrix is a diagonal matrix, and moreover, the diagonal entries are the eigenvalues of the graph. So if we call this as, say, D, then A is similar to D. Similar matrices have the same spectrum and they share several common properties. And this is an algebraic result. Every symmetric matrix is diagonalizable, and this is how every symmetric matrix is diagonalizable. And the adjacency matrix is similar to a diagonal matrix in some basis, and particularly that basis consists of eigenvectors of G. And advancing one step more, we can say that from an orthogonal basis, we can construct an orthonormal basis. Through Gram-Smith orthonormalization process, we can construct orthonormal basis, and in some case, we use orthonormal basis consisting of eigenvectors, as the case may be. Now, another observation is the minimal polynomial of the graph is a product of linear factors. Okay, that is immediate from this result, because if lambda 1, lambda 2, etc., lambda t are t distinct eigenvalues with eigenvectors v1, v2, etc., vt, then and not only v1, there are plenty associated with the lambda 1 and plenty associated with, see, there are algebraic multiplicity number of eigenvectors associated with the lambda 1 and so on. So m1, etc., mg, and these altogether forms a basis for Rn. Then if we consider the polynomial fx is equal to x minus lambda 1 into x minus lambda 2 into etc., x minus lambda t, this is the product of linear factors, and f of a is equal to a minus lambda 1 I, etc., a minus lambda t I. And you can see that this polynomial brings every element of the basis to 0, because this polynomial will bring all these empty linearly independent vectors, all these empty eigenvectors associated with the lambda t to 0 when applied here. And since A is symmetric, this product commutes also. So you can take any term, any linear term at the end and operate with the desired collection of eigenvectors. So that the minimal polynomial is a product of linear factors. Our discussions are based on connected graphs only. This is because if we consider as we stated earlier, the characteristic polynomial, the eigenvalues, these are the main concern of our topic, our discussion. And if a graph is disconnected, say with two components, then the adjacency matrix can be written as the adjacency matrix of the first component B0 and 0 the adjacency matrix of the second component. It is an elementary linear algebraic result that the characteristic polynomial of A is the product of the polynomial of this B and C. So that the spectrum or the set of eigenvalues of A is the union of eigenvalues of B and C. So the discussion pertaining to connected graph will suffice. So we discuss results concerned with connected graphs only, and for disconnected graph this can be extended component wise. This can be considered as one of the very primary results. Sum of the eigenvalues of any graph is 0. So this is because we already seen that the adjacency matrix capital A is similar to a diagonal matrix whose diagonal entries are eigenvalues. And similar matrices have the same trace. Trace is the sum of the diagonal entries. And for capital A, the diagonal entries are A, I, and all of them are zeros. So trace of A is 0, whereas trace of D is sum of lambda, the sum of these numbers lambda 1, lambda 2, etc., lambda n. So the first result follows. Sigma lambda I equal to 0. And the second one, this is actually something more significant than the first one. This gives a light to the structure of the graph. The 2m, m is the number of edges of a graph, and that is a structure property of the graph. Whereas the left hand side is purely a linear algebra term, the sum of the squares of eigenvalues. Sum of the squares of eigenvalues depends or is related to the structure of the graph via sigma lambda I square is equal to twice the number of edges. And this is also very trivial because we see already that this is for this purpose we proved the ijth entry of A raised to k is the total number of VA, VJ walks of length k. Now since A is similar to D, we can see that A square is similar to D square. So this is because from the elementary definition of similarity of matrices, A and D are similar means there is an invertible matrix capital X such that X is equal to A is equal to XD, X inverse, so that A square is equal to XD, X inverse operated with XD, X inverse. X inverse get I, so this is X D square, X inverse. So A square is similar to D square. And D square is, since D is a diagonal matrix, the diagonal entries of D square elsewhere zeros are lambda 1 square, lambda 2 square, etc., lambda n square. And trace of A square, what is trace of A square? What is the ijth entry of A square? Ijth entry of A square is the total number of Vi, Vj walks of length 2. Vi, Vj walks of length 2. Ijth entry of A square. So what is the ith entry of A square? Ith entry of A square, see that is only counted in the trace of A square. Ith entry of A square is the total number of Vi walks of length k, of length 2. Ith entry of A square is the Vi walks of length 2. Now, how a Vi walk of length 2 arise? The Vi walk of length 2 arise only through an edge incident with Vi. So, if there is an edge incident with Vi, then there is one Vi walk of length 2. So, how many edges are incident with Vi? That is degree of Vi. So, how many Vi walks of length 2 are there? What is the degree of Vi? That much number of Vi walks of length 2 are there. So, the ith entry of A square is equal to degree of Vi. So, trace of A square is the sum of those ith entries, that is sigma degree of Vi. And from the first theorem in graph theory, sigma degree of Vi is equal to twice the number of edges. So, exploring along this line gives you a relation between the eigenvalues of the graph and the structure of the graph. So, naturally, we ask for the third possibility, sigma lambda cube. So the same argument follows. A cube is similar to D cube. D cube with the trace of D cube is equal to sigma lambda E cube. And on the other hand, ith entry of A cube, ith entry of A cube is the total number of vi walks of length 3. Ith entry is vi walks of length 3. See how a vi walk of length 3 arises? You can see that can happen only through a triangle. Vi, Vj, Vk. A vi walk of length 3 can arise only through a triangle in which vi lies. See, consider one triangle in which vi lies. Then we get, see, this is one vi walk, vi, Vj, Vk, and another one is that we will get after reversing the directions, vi, Vk, Vj. See, this is another one, and this is the first one. So, a triangle in which vi lies gives rise to two vi, Vj walks, two vi walks of length 3. See, but at the same time, this triangle will be counted 2 times when we consider the jth entry and kkth entry. So altogether, a triangle will be counted 6 times. In case of vi, it will be counted 2 times, and Vj 2 times, Vk 2 times. So altogether, this triangle will be counted 6 times. So when we sum up the diagonal entries of A cube, the result is 60. So this can be pursued further. This can be investigated further to get other relations. And this sum of power of eigenvalues are called the spectral moments. Spectral moments. And the first, second, third spectral moments are trivial, very trivial. And from fourth spectral moment onwards, there are problems. So because for the ith entry of a raised to 4, the total number of vi walks of length 4 can arise in several ways. See, with the help of a k12 incident with vi, we get a vi walk of length 4. See, vi to vj, vi to vj, vj to vi, vi to vk, vk to vi. That is one vi walk of length 4. And if you traverse this vi vj 4 times, vi to vj, vj to vi, again vi to vj, vj to vi, we get a vi walk of length 4. And if there is a C4 in which vi lies, then also we get 2 vi walks of length 4. So when we consider sigma lambda I raised to 4, we should be more careful. We have to take into account more structure of the graph. And as the number of vertices and number of edges increases, an exact formula for sigma lambda I raised to 4 is difficult. But if we restrict the graph, such as a graph free from C4 or something like that, we can have some estimates for this. And this is an active area of research. What are the spectral moments? Even though the exact values are not able to be computed, what information this spectral moments gives about the structure of the graph is an interesting topic to study. Another structural relation is, or another structural property which we can deduce from the spectrum of the graph is, if G is a connected graph with the diameter D, then G has at least D plus 1 distinct eigenvalues. This is also, see, the diameter is a graph property. And the number of distinct eigenvalues is a linear algebraic property of the graph, or a spectral property, or specifically that is a spectral property. And this result then connects the structural property, the diameter, with the spectral property of the graph. See how we can see this. If G is a graph with diameter D, then G has at least D plus 1 distinct eigenvalues. So suppose the number of distinct eigenvalues is K. And we need to show that K is greater than or equal to D plus 1. And assume for the time being that K is less than or equal to D. So let lambda 1, lambda 2, etc., lambda K be the K distinct eigenvalues. And as we already seen, the minimal polynomial is a product of linear factors. So the minimal polynomial is of degree K. So the minimal polynomial is something look like A raised to K plus something, etc., plus A1 A plus A0 I equal to 0. Okay, A n A raised to K plus A n minus 1 A raised to K minus 1 plus etc. A1 A plus A0 I equal to 0, because the minimal polynomial is of degree K, product of K linear factors. Then we can see that this A raised to K can be expressed as a linear combination of I, A square, etc., A raised to K minus 1. If this A raised to K can be expressed as a linear combination of I, A square, etc., A raised to K minus 1, then any higher power, A raised to T, can be expressed as a linear combination of I, A square, etc., A raised to K minus 1. Now, it is given that the diameter of the graph is D. So, there exist two vertices U and V, such that the distance between U and V is equal to D, and there are no other path of shorter length than this D exists in G. And this UV path of length D is a UV walk of length D. UV walk of length D. So, the UV with the entry of A raised to D is non-zero, because the UVth entry of A raised to D is the total number of UV walks of length D. That is non-zero. And there are no UV walks of length D there are no UV walks of length less than D in the graph G. Therefore, the UVth entry of A raised to T equal to 0 for all T less than D. Now, this A raised to D can also be represented as a linear combination of I, A square, etc., A raised to K minus 1. K is less than or equal to D, so K minus 1 is strictly less than D. Therefore, the UVth entry of all these matrices are zeros. So, the UVth entry of the linear combination is also 0. Since because the constituent matrices have its UVth entry 0, any linear combination of these matrices also have the UVth entry 0. So, the UVth entry of A raised to D must be 0, and that is a contradiction. So, this K cannot be less than or equal to D, K should be greater than or equal to D plus 1. And this is also an interesting problem to reinvestigate. See, given a graph with a diameter D, can you characterize such graphs with exactly D plus 1 distinct eigenvalues? See, G has D plus 1 eigenvalues, so G cannot have fewer than D eigenvalues. It cannot have D or less number of eigenvalues. It can have at least D plus 1 distinct eigenvalues. Then this is a research problem. Characterize those graphs with exactly D plus 1 eigenvalues. And in fact, characterizations are already done for D is equal to 1. D is equal to 1, the graph is complete. And you can see that complete graph has exactly 2 distinct eigenvalues. And when D is equal to 2, the diameter of 2 graphs complete, that is a family of a strongly irregular graph. We can see that they have exactly 3 distinct eigenvalues. And for some D, particular D is equal to K, can we characterize? This is a problem. Can we characterize graphs with exactly k plus 1 distinct eigenvalues. Now we consider spectrum of some special matrices which we use later. A circulant matrix, and one of the most simple matrices associated with the graphs is a circulant matrix. And circulant matrix is obtained from its first row alone. From the first row, if we simply make a push, we get the second row. See an, then a1, a2, etc., an minus 1, etc. See, how can we find the spectrum of this graph? See, actually, the computation of spectrum is one of the most difficult problems in graph theory, in algebra, and even in computer science. Because the adjacency matrix associated with a graph with n vertices is an n by n determinant. And the characteristic polynomial is determined a minus lambda I. And the characteristic equation is a minus lambda I equal to 0. So, in order to find the spectrum of a graph, we have to expand this determinant. And this is an n by n determinant. And there is no easy way to expand an n by n determinant. Suppose somehow we succeeded in expanding that, then we are end up with an nth degree equation. And in fact, there are no easy way to solve an nth degree equation. So always concentrate on some other techniques to find the spectrum of a graph. And this is actually in computer language, this is a polynomially complex. The complexity of this computation is large. And we cannot, in most cases, we cannot solve an nth degree equation. There are no easy way to solve an nth degree equation. So we have to develop some other techniques to find the spectrum of a graph. And we are lucky if we have a special kind of matrices. If we have some matrices with a nice nature, we can use some other linear algebraic techniques to find the spectrum. And this circular matrix is one of such matrices. Suppose, see, you take, let omega be the nth root of unity, so that omega raised to n equal to 1. If we take a vector v is equal to 1 omega square, etc., omega raised to n minus 1, then this is an n by 1 vector. You operate with this 1 omega square, etc., omega raised to n minus 1. By a simple algebraic matrix manipulation, we can see that this is equal to the first entry is a1 plus a2 omega plus a3 omega square plus etc. plus an omega raised to n minus 1. Second is an plus a1 omega plus a2 omega square plus etc. plus n minus 1 omega raised to n minus 1, and so on. And the last a2 plus a3 omega plus etc. plus a1 omega raised to n minus 1. And you can see that if we call this as lambda, then the second entry is nothing other than lambda omega. They multiply by omega, a1 omega, a2 omega square, that comes here. And at last, a n minus 1 omega raised to n minus 2 term is there, that multiplied with omega, a n minus 1 omega raised to n minus 1. And a n omega raised to n minus 1 multiplied by omega is a n, because omega raised to n is 1. So this is lambda omega. And the next term is then naturally lambda omega square, etc. The last term is lambda omega raised to n minus 1. And this is equal to lambda v. So for a circulant matrix, the eigenvalues lambda are given by are given from the first row itself, a1 plus a2 omega plus a3 omega square plus etc. plus an omega raised to n minus 1. This can be applied to get the spectrum of some well-known graphs. We consider cycle. For the cycle, V1 on vertices V1, V2, etc. Bn. So the shape of the graph itself is cycle and the circular, and we can see that the corresponding adjacency matrix is circulant with the first row 0, 1, 0, 0, 0, etc. last one, and other rows are obtained by a simple push or simple jump of this first row. That's a circulant matrix, because if we jump from V1 to V2, again this is symmetrical as we start from V1. We start from V2 like that. So what is the spectrum of Cn? There is a collection of all numbers of the form 0 plus omega plus etc. plus omega raised to n minus 1. So this is omega plus omega raised to n minus 1, where omega is an nth root of unity. And you take, see, this is true for every nth root of unity. So if you take the primitive nth root of unity as cos 2 pi r by n plus I sin 2 pi r n by n r equal to 0, 1, 2, 3, etc. n minus 1. And if you apply De Moivre's law and simplify this, we can see that the spectrum consists of 2 cos 2 pi r by n r equal to 0, 1, 2, 3, etc. n minus 1. So this is the spectrum of the cycle. And the spectrum of Kn. So what is the adjacency matrix of Kn? The adjacency matrix of Kn, if you take V1, V1 is adjacent with all the remaining vertices. So the adjacency matrix is circulant with the first row 0, 1, 1, 1, 1, 1, etc. And the second row also, second row is obtained by a push, or V2. In V2, V2 is adjacent with all vertices except V1. So this is circulant. So the spectrum of Kn consists of all numbers of the form 0 into 1, 0 plus omega square plus omega cube plus etc. plus omega raised to n minus 1. And you can see that there are two kinds of nth root of unity. One is the real nth root of unity, that is 1, and all others are the imaginary nth root of unity omegas, given by cos 2 pi r by n r equal to 0, 1, 2, 3, etc. n minus 1. So if omega happens to be 1, then from here we get 1 plus etc. 1 n minus 1 times. So this is n minus 1. And if omega is different from 1, then we have this is equal to minus 1. Because 1 plus omega square plus etc. plus omega raised to n minus 1 is a sum of geometric series that on simplification gives 0. So omega plus omega square plus etc. plus omega raised to n minus 1 is equal to minus 1. So n minus 1 is multiplicity with multiplicity 1, and minus 1 is with multiplicity n minus 1. And similarly, the spectrum of the other two matrices, I, identity matrix is circulant with the first row 1, 0, 0, 0, etc. So the only eigenvalue is 1 with the multiplicity n. And for J is a matrix whose all entries are equal to 1. So the first row is 1, second row is all 1, etc. So that is circulant with the first row 1, 1, 1, 1, 1, etc. So the spectrum is the collection of all 1 plus omega square plus etc. plus omega raised to n minus 1, where omega is an nth root of unity. If omega is 1, then this gives rise to n. If omega is different from 1, then this is 0. So the only non-zero eigenvalue of the all one matrix J is n. And this also we use later. Another structural property we can deduce from the spectrum of a graph is a graph G is bipartite if and only if its spectrum is symmetric about 0. So we have already a characterization of a bipartite graph. A graph is bipartite if and only if it has now odd cycles. Here we can see that the graph is bipartite if and only if the spectrum is symmetric about 0. So what do we mean by symmetric about 0? When we say that the spectrum is symmetric about 0, if whenever lambda is an eigenvalue of G, minus lambda is also an eigenvalue of G. Whenever lambda is an eigenvalue of G, if minus lambda is also an eigenvalue of G, we say the spectrum is symmetric about 0. See, these kind of results, these kind of questions can be asked to other classes of graphs also. And actually, that is the way of research. If G, see here G has a particular property that G is bipartite. Okay. Then that property is characterized in terms of the spectrum. See, you should see this result in that way. G is bipartite. G is not mere a bipartite graph. G can be any graphic property, particular property P. Then can we characterize such a graph with particular property P in terms of the spectrum? So that these problems can be asked. Suppose G is Hamiltonian. Can we characterize Hamiltonian graphs, or can we have some idea, some information regarding the Hamiltonianicity of a graph in terms of the spectrum? G is Eulerian. G is planar. G is having a cut vertex. G is having a bridge. All these can be asked. And you have to use plenty of linear algebraic and graph theoretic tools to establish results. And that is research. So you should, those who want to do research, or those who want to have problems in research, think and hear these statements in that way, not as a mere theorem, mere results. So critically see this, critically think. If G is bipartite, then the spectrum is symmetric about 0. Then what happens if G is having some other particular property? If G is self-complementary, what can be? Or if G is a graph with minimum degree, say this, or if G is a graph with the number of end vertices is this much number, then how this thing get reflected into the spectrum? These type of questions can be asked, and addressing these problems, addressing these questions is the essence of research. And we prove this. This is very elementary. Suppose first that G is bipartite. G is bipartite. What do you mean by G is bipartite? The vertex set of G can be partitioned into two sets. Thus that edges are in between these two sets only. There are no edges connecting vertices of V1 and no edges connecting vertices of V2. So the adjacency matrix of G can be written as, the adjacency matrix is indexed by these vertices in V1 and V2. In between V1, there are no adjacencies, so totally 0. And in between V1 and V2, there are adjacencies. We denote that adjacency relation by B. Then in between V2 and V1, V transpose works. And between V2, there are no edges. So the adjacency matrix of G will look like a block form of this type. 0, B, B transpose 0. See, it is given, see, what we want to show is that the spectrum is symmetric about 0. So suppose lambda be an eigenvalue of G. Then there is a non-zero vector V such that there is a non-zero vector say W such that A W is equal to lambda W. See, this W works on this 2 by 2 block matrix. So W is of the form some UV. So now A W equal to lambda W means this implies 0 into U, BV is equal to lambda U. B transpose U is equal to B transpose U is equal to lambda V. So we get these two equations. Now it is given that W is non-zero. Since W is non-zero, at least one of this U or V is non-zero. Both cannot be zero. So suppose U not equal to 0. U is a non-zero vector. Then you can we consider A minus UV. Clearly, this UV and minus UV are linearly independent. UV and minus UV are linearly independent. And this is equal to 0 into minus U, BV. B transpose into minus U, that is minus B transpose U. And this is equal to, the BV, we already have lambda U. So this is lambda U. And V transpose U is lambda V. So this is minus lambda V. So this is equal to, you take minus lambda outside, minus lambda minus U V. This is minus lambda W. And this shows, this is A and this is another one, W dash. This is minus lambda W. And this shows W dash is an eigenvector of A corresponding to minus lambda, or minus lambda is an eigenvalue of capital A of the bipartite graph. So if lambda is an eigenvalue, then minus lambda is also an eigenvalue. So the spectrum is symmetric with respect to 0. And on the other way, suppose the spectrum is symmetric with respect to 0. That means whenever lambda belongs to spectrum of G, minus lambda also belongs to spectrum of G. And we need to show that G is bipartite. In order to show that G is bipartite, it's sufficient to show that G has no odd cycles. And as we discussed earlier, see this sigma lambda I raised to k, where k is odd, is the total number of VI walks of odd length. Sigma lambda I raised to k is the total number of VI walks of odd length. If k is odd length k. But what is this? We know that whenever a lambda raised to k appear in this sum, there is a minus lambda raised to k appear, because whenever lambda is an eigenvalue, minus lambda is also an eigenvalue. So these two terms cancel each other, so that their sum is equal to 0. So the contribution of this sum is 0. Therefore, the total number of VI walks of odd length equal to 0. We know that suppose there is an odd cycle. An odd cycle is a walk of odd length. The total number of VI walks of odd length is 0, means there are no VI odd cycles. So the total number of odd cycles in the graph is 0, or the graph is free from odd cycles. Therefore, the graph is bipartite. So this is how the spectral tools are used to establish some results. G is bipartite if and only if the spectrum is symmetric with respect to 0. And this is the classical Perrin-Frobenius theorem for a k-regular graph. See, this is the theorem. If G is a connected k-regular graph, then the all one vector is an eigenvector corresponding to k. And for a connected k-regular graph, this k is a simple root of the characteristic polynomial, or the algebraic multiplicity of the eigenvalue k is 1. So that can be proved by showing that the dimension of the eigenspace of k is 1. And if lambda is any other eigenvalue of G, then lambda lies in the interval minus k. So we show one by one. This is simple to show. What is the first observation? If G is k-regular, suppose G is k-regular. This G is k-regular. See, consider any row. Vi is adjacent with k vertices. So there will be k ones. K ones in each row. K ones. So if we multiply this with the all one vector, 1, 1, 1, 1, etc., we can see that this is first row into this is the first row sum. So the first row sum is k. Second row sum is k, etc. K. So this is k into 1, 1, 1, 1, etc. So A into J, J is the all one, n by 1 column matrix is equal to k, j n by 1. Therefore, for a regular graph G with regularity k, the regularity k itself is an eigenvalue. And now we can show that the dimension of the eigenspace associated with k is 1. We can show that k is a symbol. K is a symbol means the number of occurrence of k as an eigenvalue is 1. We can prove that by proving that the dimension of the eigenspace or the number of linearly independent eigenvectors associated with the k is j is 1. All other eigenvectors are multiples of this j. You do that like this. See, suppose x is equal to x1, x2, etc., xn be any other eigenvector of k. Any other eigenvector corresponding to this k. Then, without loss of generality, we assume that at least one entry of this x is positive. Because if all entries of x is negative, we take minus x instead of x. So at least one of these entries is positive, and let xi be xj be the largest entry. Xj be the largest entry. And we know that now Ax is equal to Kx because x is an eigenvector corresponding to k. So suppose Vj1, Vj2, etc., Vjk be the k vertices adjacent with Vj. Now expanding this along the jth row, only for those vertices, the corresponding entries xj1, xj2, etc., xjk need to be counted because for all others, aij equal to 0. So the only non-zero row entries in capital A are aj1, aj2, etc., ajk because vj1 is adjacent to vj, vj2 is adjacent to vj, etc. So expanding along the jth row, we get xj1 plus xj2 plus etc. plus xjk is equal to kxj. And xj is the largest entry. So all these xj i's are less than or equal to xj. Now none of them can be less than xj. Because if one of them is less than xj, then to keep the sum of these k numbers as kxj, some other entry will be greater than xj. And that is impossible. None of the entries is greater than xj by the same reason. So all these entries, xj1 equal to xj2 equal to etc., all these entries should be equal to xj. So now in this eigenvector x, we get several largest entries. Now we apply the same argument to these entries. We can show that this eigenvector x is nothing other than xj, xj, etc., xj. So that is, it is a scalar multiple of the all one vector. It is a multiple of xj. So there is only one linearly independent eigenvector. This all one vector is already an eigenvector associated with K. And all other eigenvectors are scalar multiples of this. Therefore, all these are linearly dependent. So the dimension of the eigenspace associated with the K is 1. Okay. So the geometric multiplicity of the eigenvalue K, that is 1. So by our last result, algebraic multiplicity equal to geometric multiplicity, K is a simple eigenvalue of the graph G. And this result is of profound significance in our later discussions. And by a similar argument, we can show that if lambda is any other eigenvalue of G, then minus K less than or equal to lambda less than or equal to K, by showing that modulus of lambda less than or equal to K. So that is also a simple argument like this by taking an eigenvector corresponding to lambda and with the largest absolute value, we can show that. So see what is the advantage of this Perron-Frobenius theorem for a K-regular graph? See, if G is K-regular, then we need not go beyond the closed interval minus K to find the spectrum of G. The spectrum of G is fully contained in this closed interval minus K. And even it attains its supremum K. So then this is a research problem. So given some particular K, can we characterize those graphs whose spectrum lying in between those K, those minus K and K, in the closed interval minus K. And the same can be asked for irregular graphs also. So the treatment of irregular graph is little more difficult than regular graphs. That also we will see during our discussion, if we have a time for discussion for that also. So the same question can be asked in case of irregular graph also. What can we say about, what information we can have about the spectrum of an irregular graph or a semi-regular graph? Do the spectrum reaches at a more simpler level than an irregular graph? Yes, of course, because there are only two type vertices of degree, say S and T, those vertices with S and those vertices with the degree T. So these type of questions can be asked, and there are several results concerned with spectrum of irregular graph also. And another important result regarding the spectrum of graph is the Hofmann polynomial theorem. Suppose G is a K-regular connected graph on n vertices, and this result uses the results we have discussed so far. Suppose G is a K-regular and connected graph on n vertices. First I say, what is this? Adjacency algebra of G. Suppose A is the adjacency matrix of G, and the collection of all polynomials f of A, where fx is a polynomial with real entries. The collection of all matrices of the form f of A constitute the adjacency algebra of G. So you take polynomial in X with real entries, then f of A. There is an infinite number of such matrices because there are an infinite number of polynomials. The collection of all such polynomials is known as the adjacency algebra of G. And Hofmann polynomial theorem states that a graph G is regular and connected if and only if J, the all one matrix of order n, is in the adjacency algebra of G. So that is, for some polynomial fx, f of A is equal to J. I hope this is clear. Adjacency algebra of G is a collection of all polynomials of the form f of A. So J is a member of this adjacency algebra means there is some polynomial fx such that f of a is equal to j. Okay, so we assume first that j is in the adjacency algebra. So suppose j belongs to the adjacency algebra of G. What to show is G is regular and connected. So first we prove G is regular. See, how can we show that a graph is regular? We consider the adjacency matrix. If each row sums to a constant, say k, if the sum of each row is k, then we can see that there are k ones in each rows, so that each vertex is adjacent with k other vertices, so that the graph is regular. So to show that the graph is regular, it is sufficient to show that each row sums to a constant. So now we consider Aj. What is Aj actually? In the computation of Aj, we are computing the first row sum when we multiply A with the first column of J. If we multiply the first row of A with the first column of J, what we are getting is the first row sum. Second row, first column is the second row sum, and so on. Now Aj is AFA. Because since J is in the adjacency algebra, there is a polynomial fx such that J is equal to f of A. Now since A is symmetric, this A and FA commutes. So this is f of A. F of A is J. So this is the same as 1, 1, 1, 1, etc. A. So what is the first row sum? First row sum. First row, first column of J, that is the first row sum. That is equal to first row of J with the first column of A. That is the first column sum of A. That's C1. Second row sum R2 is equal to the second row sum. Second row of J with the first column of A. That is again first column sum. That is C1. Similarly, R3 is equal to C1, etc. Rn equal to C1. That means each row sums to the same constant C1. So the graph is regular. If C1 is K, then the graph is K regular. And the graph is connected also. So assume the graph is disconnected. What happens in a disconnected graph? See, assume that G is disconnected. We want to show that the graph is connected. If it is disconnected, see, take two vertices, U and V, from two different components. Then there exists no UV walk of any length. No UV walks of any length. So if we take the ijth entry of any power of A, the ijth entry of A raised to K, not ijth entry, the UVth entry of A raised to K is 0 for all K. K equal to 1, 2, 3, etc. See, if the UVth entry of A raised to K equal to 0 for all K, then the UVth entry in any polynomial in A is also 0. UVth entry of A raised to K is 0 for all K. So you consider any polynomial. Any polynomial is a linear combination of powers of A. In those powers, the UVth entry is 0. So the UVth entry of the polynomial is also 0. But there is a polynomial J which is equal to f of A. So the UVth entry of J is also 0. And that is impossible. Therefore, G cannot be disconnected. Therefore, G should be necessarily connected. And on the other way, assume that G is K regular and connected. Since G is k-regular, we know that K is an eigenvalue by Perrin-Frobenius theorem. As it is connected, K is a simple eigenvalue, again by Perrin-Frobenius theorem. And suppose K, lambda 2, lambda 3, etc., lambda t be the distinct eigenvalues of G. And these eigenvalues are distinct from K. Then we know that the minimal polynomial f of x, minimal polynomial is x minus k into x minus lambda 2 into etc. x minus lambda t. See, if we call this as gx, then this is x minus k gx. Therefore, f of a is equal to a minus ki ga. And since fx is the minimal polynomial, fa vanishes. So this is 0. Therefore, a minus ki ga equal to 0 implies a ga is equal to ki. This then means this is a ga, this is ki. This then means each column of ga, is an eigenvector of A corresponding to K. See, because when we multiply this A with the first column, we get the first column of I multiplied by K. This is GA, KGA. This is GA, sorry. So when we multiply the first column of GA with A, we get K into first column of GA. So A into first column of GA is equal to K into first column of GA. So each column is an eigenvector of A corresponding to K. And by Perrin-Frobenius theorem, we know that any eigenvector of A corresponding to K is a scalar multiple of the odd one vector. Therefore, the columns of GA are some C1 j n by 1, C2 j n by 1, etc. Cn j n by 1. So GA will look like C1, 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 etc. C1, C2, C2, etc. C2, etc. Cn, Cn, etc. Cn. But A is symmetric. Therefore, GA is also symmetric. So the first row coincides with the first column. Therefore, every Ci's are equal. Therefore, C1 equal to C2 equal to etc. equal to Cn equal to C1, or let it be C. So all the entries of this GA, so GA is equal to C, etc. So this is C1, 1, etc. 1. So this is Cj. What was Gx? So there exists a polynomial Gx such that Gx is equal to x minus lambda 2 into etc. x minus lambda t, such that G of A is equal to Cj, or 1 by C Ga is equal to J. So there is a polynomial, say Hx, such that HA is equal to J, where Hx is equal to x minus lambda 2 into etc. x minus lambda t by C. Now, how to find? See, this is the Hofmann polynomial theorem. There exists a polynomial Hx such that Ha is equal to J. And what in fact this polynomial is? See, what is H of A? H of A is equal to A minus lambda 1 I into etc. A minus lambda Ti. Hx is equal to x minus lambda 2 into x minus lambda 3 into etc. x minus lambda t by C. And this is equal to J. Now h of a is equal to a minus lambda 2i into etc. a minus lambda ti by c. That is equal to j. This is not j. ha is equal to j. Since this is a polynomial in a, corresponding to every eigenvalue lambda of a, h lambda is an eigenvalue of this expression. Now we can see that the eigenvalues of a are k, lambda 2, etc. lambda t. And corresponding to lambda 2, h lambda 2 is 0. H lambda 3 is 0, etc. H lambda t equal to 0 because of these type of factors. So, corresponding to these eigenvalues, we get only 0 eigenvalue of h of a or that of j. And corresponding to the eigenvalue k of a, hk is a non-zero eigenvalue. Hk is equal to k minus lambda 2 into etc. k minus lambda t by c. And this is, in fact, the non-zero eigenvalue of j. See, when we discussed the circulant matrices, we proved that n is the only non-zero eigenvalue of j. Therefore, we get to c as k minus lambda 2, k minus lambda 3, etc. k minus lambda t by n. So, specifically or particularly, hx is then equal to hx is equal to x minus lambda 2 into etc. x minus lambda t by n by c. And c is k minus lambda 2, k minus lambda 3, etc. k minus lambda t by n. So this is n. So we showed that the Hofmann polynomial p, this hx, here in the theorem it is notated as p. Okay, whatever it may be. The Hofmann polynomial hx satisfies the condition that h of a is equal to j. So when we see, the advantage of this can be seen when we expand the characteristic polynomial and we see that a j factor appears there. And that j factor can be replaced by a polynomial in a. That is the advantage of Hofmann polynomial theorem. And in addition to that, hk, what is hk? Hk is equal to n because n into k minus lambda 2 k minus lambda t by this two cancels, and hk is equal to n. And h lambda equal to 0 for any other eigenvalue lambda different from k of g. And this is the Hofmann polynomial. See, this technique, this Hofmann polynomial technique, this result can be effectively utilized to find the spectrum of some classes of graphs. See, one of such classes is, suppose G is a regular graph. Suppose G is k-regular with adjacency matrix capital A. Then what is the spectrum of, suppose the spectrum of G is not, can we find the spectrum of its complement? The complement has adjacency matrix A complement. A complement is the adjacency matrix of G complement. And we know that two vertices in G complement are adjacent if and only if the corresponding terms are not adjacent in G. So whenever Aij equal to 0 in G, the adjacency matrix of G, Aij equal to 1 in A complement if Aij equal to 0 in A, and vice versa. And the diagonal entries are zeros. So we can see that the adjacency matrix of G complement is something like J minus I minus A. And this J can be replaced by a polynomial in A minus I minus A. And this is a polynomial in A, and Hofmann polynomial theorem can be applied. Corresponding to the regularity K, we get Pk is equal to n. N minus 1 minus K is an eigenvalue. And for K different from that, E lambda equal to 0. For any other eigenvalue, this term is 0 and the only contribution is minus 1 minus lambda. I think I took 15 minutes more. Sorry, I thought that I can extend up to 5:30. That is why. Okay. Yes. Sorry, I am sorry for the inconvenience. So let us stop here. And there are many more things to be explored, which uses some linear algebraic techniques to explore the spectrum of graphs. Okay, thank you. If I have any questions, you can ask.
So we will continue on 17th, as already announced.
Okay.
17th, what time, sir? 3:30 or?
The morning session will be appreciated, sir.
Okay. Sir, for incidence matrix, can we apply all these techniques for incidence matrices?
Yes, sir, the problem is, for an incidence matrix, the incidence matrix is not a symmetric matrix.
Okay.
And that is a P by Q matrix if the graph has P vertices and Q edges.
Okay.
And the incidence matrix theory uses the singular values of the matrix.
Okay.
So instead of eigenvalues, we cannot find the eigenvalues of the incidence matrix.
Right.
So if capital I is the incident matrix, then instead of the eigenvalues, we use the singular values of I. Which are the eigenvalues of the matrix I transpose.
Okay.
That will be a P by P matrix.
Right.
And also the singular values of I transpose I, if I is the incidence matrix. And the spectral theory along that line can be developed, and also it has already developed, and further research can be done by replacing this adjacency matrix with the incidence matrix. Any questions?
Any other questions?
Okay, sir, can you suggest some reference books for further reading? Yes. I think I can give that towards the end of the next session. Otherwise, you read the Spectra of Graphs book by Chetovic, Dubs, Sashes and Dubs, and Eigenspaces by the same authors. Spectra of Graphs by William Hammers. And more than these textbooks, there are plenty of papers available in the repositories, in several repositories dealing with one aspect or other of the spectrum of graphs. Can you give some motivation for this study? Motivation, you mean the applications, I think. Yes. See, there are plenty and plenty of applications